Why do certain metal alloys break differently? Imagine two metal objects, one bending easily and the other snapping suddenly. Why do they behave so differently even if they look similar? The answer lies in how their internal structures and compositions influence their failure. Metals are made up of tiny crystals called grains. The size, shape, and orientation of these grains affect how the metal deforms and ultimately breaks. Some metals can stretch a lot before breaking, showing ductile behavior. Others fracture quickly with little deformation, which is called brittle failure. This difference depends on the alloy's microstructure and how dislocations, defects in the crystal lattice, move under stress. Alloys are made of different phases, regions with distinct crystal structures or compositions. These phases influence strength and how the material fractures. For example, alloys that are hardened by small particles, called precipitates, block dislocation movement. This makes the alloy stronger but less ductile. Sometimes, these phases can also act as crack starters, leading to brittle fractures. The way dislocations behave during deformation also matters. When metals deform, dislocations move and multiply, causing strain hardening. Some alloys harden gradually and maintain strength over many strains. Others soften early, leading to quicker failure. Different alloys are prone to specific failure modes. Fatigue occurs when repeated stress causes tiny cracks that grow over time. Creep is slow deformation under constant high temperature and stress. Stress corrosion cracking happens when a corrosive environment and tensile stress combine, causing cracks along grain boundaries. Hydrogen embrittlement involves atomic hydrogen weakening the metal, making it brittle. Liquid metal embrittlement occurs when a liquid metal, like mercury or aluminum, causes rapid cracks along grain boundaries under stress. These failure mechanisms depend heavily on the alloy's chemistry and the environment it faces. Grain boundary characteristics also influence how and where cracks start. Some alloys have grain boundaries that resist crack growth, while others are more vulnerable. Cracks can propagate along grain boundaries, called intergranular fracture, or through the grains, called transgranular fracture. The chemistry and structure of these boundaries determine how easily cracks spread. Environmental effects play a big role too. Corrosive environments can weaken specific parts of an alloy. For example, chloride-rich environments can cause pitting corrosion or stress corrosion cracking in stainless steels. This localized attack can lead to sudden brittle failure. Understanding these differences helps engineers choose the right alloy for each job. For example, aerospace parts need alloys that resist high temperatures and creep. Medical implants requiring alloys that resist corrosion and wear inside the body. In the end, how an alloy breaks depends on its internal structure, how it deforms, the failure mechanisms it's susceptible to, and the environment it's exposed to. These factors combine to create unique fracture patterns, and knowing them helps prevent unexpected failures in real-world use.